Hi, I'm Andy. Today we're going to parse SGF files in Rust. So an SGF file is a way of describing a game, especially used for Go games. Go is the best board game that there is. Here's an example of an SGF file. There are several Rust SGF file parsers on crates.io. So this isn't going to be a real thing. This is just for fun. I have a vague ambition to write some kind of Go. I do love Go and I love Rust. And I have some ambition to write a Go thing that can talk to various Go servers. Maybe even make an Android app, because the current Android apps are not great, but making Android apps is so awful that maybe not. Anyway, so to start on that would be to understand the format that the Go games are often exchanged in, which is this SGF format. So here's one example. This is a game that I'm currently playing. There are also some examples on the SGF file format website. So basically, it's like brackets around things, and then if there are different variations of like different possible ways the game might go, like this is how the game actually went and this is what you could have done, then you end up with another set of brackets inside the main set of brackets. And here's another set of brackets. So basically this is the format, and just for fun we're going to figure out how to parse that format. So since there are some things on crates.io that already do this in a sensible way, we're going to have to think up a silly name. So if I could type, so I'm going to call it like Super Go I don't know, it feels like it should be a fuller word. Super Go flower. Super Go flower. Fine. That's what we're calling it. So let's go into our Super Go flower directory there, and let's open up our Rust code. All right, so currently we have nothing. Let's write some tests. So the simplest test, well, there could be, I don't think an empty file is technically a valid SGF file. So let's not have that. Let's have an empty game tree, I think they're called. I'll show you the documentation in a second. Right. So let's just say empty game tree parses, even if that might actually not be valid. So let me show you the docs. So this is probably enough for us for now. So an SGF file is a collection, and that means a game tree and any number of more game trees, where a game tree is a bracket and then a sequence of things and possibly more game trees inside, because it's like a nested collection of bracketed things, as we saw. And look, here's my answer. A sequence is at least one node followed by any number of other nodes. So actually this empty game tree is not going to be technically allowed, but we'll live with that for now. We're going to make ourselves, I guess we're going to have something called something like, well, hang on. First before we parse, we're going to lex. So let's just do lexes. So we can lex an empty game tree. I'll explain what lexing and parsing are in a second. So we're just going to say let tokens equal lex. So we're going to lex something. Whoops. And what we're going to lex is bracket. And then we're going to assert that what we got out of that. Should we do any streaming, or should we just have it return a vec? Let's have it return a vec and see if we dislike that, because these SGF files are so small that it's probably fine. So this is going to be a vec of tokens. So there's going to be some kind of thing called a token. And let's just say it's going to be called token open bracket and then token close bracket. So these things don't exist yet. None of this exists. None of this compiles. But this is approximately the structure we want for our program, I think. So when we lex a string like this, we're going to get back a bunch of tokens. And in this case, there's going to be an open bracket and a close bracket. So it's overdue for me to explain what lexing is. All right. So lexing is basically the word for going through some kind of string input like this and turning it into like chunks of, well, I guess they're just like groups of characters. In this case, single characters, just an open bracket and a closed bracket, but other bits of lexing will end up swallowing up a bunch of characters into one thing that we call a token. And not understanding them, just like classifying them. Right, so that's probably enough for now. Well, and then it will hopefully become clear. So we're going to get the lex function from out of here. And it's going to take in, I mean, for now, let's have it take in a string reference and return a vec of token. And we'll see whether any of this wants to be done with iterators or anything like that. But I'm thinking not, because like I say, these files are quite small. And let's just return an empty vec for a second. Yeah, these files are never going to be anything that bothers the memory of any computer made in the last 30, 40 years. So should be fine to just assume it's all in memory and there's no streaming needed. Fine. All right, and I guess we want to use this function in our main method just to make our life easier. So let us just say, let's just print out something that we've lexed. So let's lex something more interesting here, shall we? Like one of the example strings is probably a good idea. Let us just try lexing this thing. Like so. Yeah, it's not got any nested stuff in it, so it's probably not a great example, but it'll do for now. And now to make this compile, we're going to need an enum called token. And it's going to need a variant called open bracket and a variant called close bracket. Now I think, yeah, all right, not quite. So well, tokens need to be at least debug printable for us to do this. So let's make this derive debug, which is also needed for the assertion to work. So that's convenient. And it also needs to be comparable. Otherwise, we can't assert that two things are equal if we don't know how to compare them. So partial equal just gives us a way of comparing them. Complains that it's not used, but that's okay. They'll be used soon. Right. So now we can test this. Whoops, like so. And the tests fail. And let's just check that we can run it as well. So it gives us some warnings. It runs and it says, oh, you've got back an empty vec, which is fair enough because we have. So we're gonna make this test pass. So right now we return an empty vector, and we should be returning open bracket, close bracket. And to do that, we're actually going to do some lexing. We're not just going to completely cheat, even though test-driven development demands that we not exactly cheat, but do the minimum thing. But in this case, I think the minimum reasonable thing is actually to walk over the input, I think. So let's just say for char in input.chars. Now there's some question about this because our input is not UTF-8. So really our input shouldn't be in _str. It should be a slice of U8s, which we can make by just saying, actually we can make that by just saying, putting a B there to say, treat this as UTF-8 and turn it into bytes. And in this case, there's no, because all of this is just ASCII, there's no difference between the input that we might be expecting and the UTF-8 representation of it. So the input that we're actually expecting here is generally mostly ASCII, but then you can have strings inside some of these square brackets which are of different char sets, which is like the older idea of how you did characters before Unicode. I've got a great video called Interesting Characters, which talks all about character sets and Unicode and things like that, and tells you why you should love UTF-8 and hate UTF-16 and so on and so on. Not just hate UTF-16, but resent UTF-16 for ruining everything. Anyway, that's not what we're doing here. So this is all a roundabout way of saying, in between these square brackets, sometimes there are things which are not ASCII. They'll be in some char set. So there'll still be 1 byte per character, but those bytes are different depending what char set it is. So it might be, say, Greek, the Greek char set, which means a particular number like 150 would mean a particular Greek character or something like that. So the point is, yeah, we have to pass this in as bytes if we're going to deal with that later. So U8s are just 8-bit things, so bytes, but we won't deal with it now, and it's fine for us to just say, turn the following UTF-8 into bytes, which is what this B means, because it's all just ASCII. That was me just waffling on about something you don't care about. Okay, so let us very quickly copy in my rust format.toml, because I can't live without it. And that'll format my code for me nicely. Okay, right. So, okay, where have we got to? We're looping through all the characters. And for each character, we're just, for now, we're just going to match. So no, okay, so input.charge doesn't exist anymore. So instead, we're looping through all the bytes. I guess I'll call that B. We're going to do a match on B. And if B is a byte that it looks like the ASCII for an open bracket, then we're going to return an open bracket. Yeah, so return is the wrong word here because I've missed something. Something I'm doing here isn't quite working yet, so that's okay. And if it's a close bracket, we'll return token close bracket. But actually what it should be is we're going to add this to some kind of vector. Like so, and then return that at the end. Whoops. Where are all these spaces between things? That's better. Okay, and so once we've got hold of this thing, like this, we're going to put it into our return. Okay, and also it might be something else. So if it's something else, I guess we're going to have to do some kind of error handling. So we'll immediately stop, return an error of type parse error, which I guess, it's lex error, which I guess we're going to need to define. And this is like invalid character. And it's going to be, let's provide the character, which is B. Should we maybe pretend that this is some kind of named, so it has character B, and in principle it should have like a line number and a column number.
So let's imagine we've got line and column numbers that we can provide in our error messages as well. And I guess then we'll count their columns and lines like this. So line number is going to start off as 1, and column number is also going to start off as 1. Every time we move forward one character, we're going to modify column by 1 for now. And then there's probably some kind of like should do more here. And this is probably the wrong place to do this as well, because sometimes we'll be pulling in more than one. Deal with multiple characters and new lines. Something like that. Okay. Alright, so it's not happy because this doesn't actually return a result, and it should. So it's going to return a lex error, which again is something we just imagined exists. We better make it exist. And have this thing called invalid character, which has a character, which is a U8, because actually it's not really a character, it's a byte. And it has a line, which I guess is a U size, and a column. Should it be a U size? It doesn't matter, fine. Alright, what are you moaning about? Oh, I found a reference to a U8. We can deal with that. Okay, are we compiling? No, because this is now returning a result, so we need to do that. And yes, fine, line, it doesn't need to be mutable yet. And now we need to unwrap after we do our lexing, because it now returns a result. Oh, and lexing error doesn't implement debug. And we should implement partially as well, because I want to do some assertions about our errors. At least in principle, I want to show how we can check our error code as well as our non-error code. So let's just test that right now. And we'll check that it gives us the right, at least the right column number. Invalid byte is an error. So, alright, just some kind of byte that just shouldn't be the first character. In fact, let's not have it be the first character, let's have it be the second character. That's at least something. So something that shouldn't be the second character in our thing. I think it needs to be a semicolon next. Is that right? Certainly, I haven't seen any question marks being allowed here. Yeah, like node, there is always a node, and node always starts with semicolon. So actually, it's not really an invalid character, it's just an unexpected character at this position. I think unexpected character is a better name for what we mean here. Unexpected character. And actually we can say expected should be semicolon, right? Because in this position, well, no, I tell you what, that's not really right. We expected open bracket in this situation. Yeah, that's rubbish. Okay. Now this isn't yet sensible, because it actually depends on like what we're currently doing, what we expect. So this is all right. No, this is a bad idea. I've started parsing. Someone pull the emergency alarm. We're not going to say what we expect. What lexing does, no, I think invalid character is better. What lexing does is breaks us up into chunks, as I said, and doesn't understand.
and therefore doesn't have a great deal of context. Like what it does have context about, okay, so for example, if you're lexing some kind of programming language, it will have the context of, okay, I've seen an opening quote or a double quote, so for now I'm looking for the rest of a string, and then when I see another double quote, it'll be the end of the string. It has that much context, but it doesn't have any context about what I was about to do there, which is like, we're inside an open bracket, therefore the next thing should be a semicolon. That would be the parser that has that type of context. Okay, in that case, let's have a character that should never appear anywhere. So let's try lexing a question mark. I think that's probably not allowed. And then we're not going to unwrap it. We're going to unwrap error it, because we expect this to return an error. And then we're going to assert that the error is a lex error, invalid character, and the character is going to be question mark, and it's on line 1 and it's on column 2, just to at least have some testing around that error checking code. And I guess when we start handling new lines, we're going to want at least one more thing. Right, when we run that test, that also passes, which is scary. I think should never pass first time. So let me just see it fail. And the failure message looks okay, so fine. I don't know whether I'm going to regret having this character be a U8. We could somehow like convert it to a Unicode char, but let's not do that for now. We'll see how it works out. All right, so we have got one thing lexing okay. But we need to lex some more stuff. So let us lex some kind of more realistic thing, like maybe, is this thing too unrealistic? Let's try lexing that whole thing. Like, I'm in a bit more of a rush today than usual. I kind of want to like get this working. I don't know if that's at all reasonable. So a small game lexes, and it's going to lex into an awful lot of tokens. So it's going to be an open bracket, and then semicolon, and then I think we're going to call it a symbol. No, hang on, there must be a word for this. It seems to me that it's a prop ident. I think it's a prop ident. Let's try calling it a prop ident. Prop ident. Which is good, basically any string that's outside of square brackets is going to be a prop ident, I think. And this, yeah, the point is this is always going to be ASCII. So it's going to be a prop ident with FF in it, but it's going to be the binary. No, I guess we can because we know it's going to be ASCII, we can actually parse that. We can treat that as, we can parse it as ASCII and then treat it as Unicode. And then there's going to be now what do we call this thing? Square bracket and then some stuff and then square bracket. It is a prop value. Okay, so it's a prop value. And that is going to, I don't think it needs the square brackets, but this is going to stay as bytes because we don't yet know the character encoding. And then there's another thing. So I think we should delete some of this because there's a ton of it. But we should definitely allow, in our example, there to be multiple properties before the next semicolon. So let's have another one. So this is another prop ident. And this has GM in it. And then, so we may find that the way I've done this with prop value being like the whole square bracketed thing being all one thing might turn out to be wrong. Let's not do GM. Let's do the SZ because it's got 2 characters in its prop value. So let's get rid of GM. Just have SZ. And then we'll have just one move by black will do us. That format's slightly nicer. So we've got FF, SZ, and then a semicolon. Not there, there. And then a move by black, which is a B, and an AA. Alright, so this was all just fantasy because none of these things exist. So let's have those variants. So there's one called semicolon. There's one called prop ident, which holds onto a string. And there's one called prop value, which, as I said, could be in some other char set, so it's best to hold that as a vec of U8, I think. Stop moaning. Right, so what are you moaning about now? Okay, this needs to be a string. Like so. We could build some kind of constructor function that means we don't have 2 owns all through our tests. We'll see about that. And now this needs some kind of 2vec. Yeah. So this is the B and then double quotes, that makes us a slice of U8s. And then there's a convenient 2vec method on that, which will give us a vector. The reason I've made it hold on to a vector instead of a slice or something like that is if we had a slice or an ampersand str here, then there would need to be a lifetime on this token, which actually maybe is. If we just took always took references to slices of U8, these tokens wouldn't actually need to own any memory at all. They could just refer to parts of this original input using reference semantics, which would be kind of cool in terms of not using much memory. And certainly for where we're referring to slices of U8, it would work. Where we're converting to string, it wouldn't work. So I think I'm not going to do that because, as I said, I want to get things done. And owning stuff is just a lot simpler than referring to stuff and having to make sure that lifetimes and stuff are okay. All right. So it went wrong because there was an invalid character, which was the character 59, which I guess is semicolon, but that is rather annoying. Okay, so I'm already regretting not turning this character into a char. But then there won't always be that character. I could. Right, I'm not going to worry my pretty little head about it. Instead, I'm going to ignore it. All right, so if we find a semicolon, we return semicolon. But we're getting to the interesting part soon. So I guess the first interesting part is if we hit a character that is not just a single, it might be multiple characters, we need to do something more than just this one, like the one-to-one correspondence between a byte and a token. So here, if we find something that is anywhere in the range A to Z, I don't know if it's convention or enforced that this has to be a capital letter. UC letter gets defined somewhere. Where do we define U? Oh, it's just capital A to capital Z. Fine. Oh yeah, that's what UC stands for. I got it right. Okay, so prop idents are just uppercase letters. So that means A to Z. This ... equals means that Z is included in that range. Now it's not just going to return a token. It's going to slurp up more characters and then return a token. So it's going to be something like prop ident, but we need to grab more characters. Oh, and then, yeah, so maybe iterating through bytes is just a better way of doing this, because I'm used to, like, what am I going to do here? I have to, like, somehow skip forward. Yeah, so I should definitely be iterating here, and then pass the iterator in to here, to whatever function I'm calling, so it can read more, it can suck more characters out of there. So I guess for now we can turn this into an iterator. In fact, what we should do is just do a do loop, I think. No, loop is called, isn't it, in Rust? Right, yeah. Let's have an iterator through input like so. And then we're going to take the next thing, which means this needs to be a mutable thing, obviously. Now, and that returns an option. So I guess it's going to be, if we got something out of that iterator, do this. Otherwise, no, hang on, that's the end of the loop. Otherwise, we're going to break. But that's not the only reason we might break. Oh, I hate this. Why do I hate this so much? It's awful. Oh, stop popping up in front of me so I can't see. Oh, no, I was right first time. That was not that's the if there. But it doesn't like me for some reason. So we're looping through. Oh, I'm talking, okay, what I'm doing is total rubbish. What I should be doing is, if so get hold of the next thing from the iterator. If it is something, then match on it. Like so. And then that's why I was so confused about where the curly brackets were, because I didn't actually have enough, because now the match needs to be inside. And then if we got something out, I guess, then we push the token in here. And this shouldn't be called token. What on earth am I doing? This should be called byte, or B. Yeah. All right. Are we finally somewhere near something that's quite reasonable? So if we've got anything from the iterator, get the next token, and then push the next token into our return value. If there's no more, then break. So we're kind of manually implementing a for loop, right? Like, we call next on the iterator, and if there's nothing, we call break, but there might be other reasons maybe to break. Or, yeah, it feels weird. Yeah, the point is we're advancing the iterator in places other than here. We're about to. So it feels weird to me to have a for loop. I think a for loop would kind of work. But yeah, I hate this. I hate this all so much. Right, so I hope that some better structure will come out of this. So now we're going to have another function called lex prop ident, and it's going to take in the iterator because it's going to iterate through some more stuff, and it's going to take in b because we've found the first character of this prop ident, and it's going to return, I guess it's going to return a result, and hopefully if all goes well, lex prop ident will return you a string, and it will have moved the iterator on a bit. We need to pass in a mutable reference to that iterator. Alright, so here's our function. Generate it for us, please. Thank you. And it's going to return a result of, what did I say? String or lex error. And basically what it does is it goes through until it finds, oh, you know what? We've got this problem that I had last time I wrote code like this, which is this iterator. We're gonna suck up a byte from this iterator, which we actually want to use next time round this loop. So I kind of want to be able to put things back into the iterator. So we're going to need to implement that again, or can we peek? We can make maybe a peekable iterator. Yeah, let's do that. Okay, so how do you make a peekable iterator? Is there something just going to do that for us? No, we probably need a crate for that or something. I don't want to add a dependency. Instead, I want to just do it my way. So what I'm going to do is I'm going to make myself an iterator class called putbackable iterator. What do we call that? I had a good name for this because if you've been watching all my videos, you've seen me write this some other time. Let's call it myiter before I explode. So there's going to be a struct called myiter, which holds on to an iterator of bytes. It's going to hold on to whatever into iter returns, which is some kind of depends on. It's going to return it. It's going to hold on to a core slice iter. Really? Or it could hold on to. Why doesn't it just hold on to a slice of U8s? So let's not call it myiter. Let's call it like it's like a. It's going to own. Yeah, it's can't talk. It's going to hold on to a slice of U8s and it's going to move through them. And let's call it a move through. And it's going to, yeah, as I said, it's going to have a lifetime because it holds on to a slice of U8 called bytes. Like so, and it's going to hold on to, I mean, now we could just have an index into that slice, couldn't we? And implement our iterator like this. So this should be just a usize. And it's going to have a next method, this thing. Which returns an option of, it takes in a mutable reference to self, and it returns an option of U8, or maybe reference to U8, but since we know it's a U8, then it's simpler. So yes, let's call this move through. Really got to find a better name for that. But the problem is it's kind of not an iterator, but it's an iterator. Let's have it return none for a second, not 9. And this also needs to know about these lifetimes.
In fact, I could probably get away with that. Yeah, we don't actually need to say what the lifetime is for this method. Yeah, at least. So, we don't have a new. Let's make a new. Takes in a slice of U8. Now I think we do need the lifetime to be named because we're talking about it there. And it returns one of these things. This should, obviously, this is like, I haven't named it. This should be bytes, I guess, because that's what we called it here. And the index starts off at 0. I can type that. So we make a self. It's got the bytes in that we've been given, and the index starts at 0. And when you call next, it will move the index on. That means this is now just a U8. And yeah, so Lex prop ident takes in one of these move through things now. So let's just call it bytes. I guess it's taking a mutable reference to that move through. And let's have it return something. For now, not a lot. It should at least have B in it, though, really, shouldn't it? And maybe this should be a char, but we'll think about that. Okay, so where have we got to? We made this iterator thing, but it doesn't actually do anything. I would normally write unit tests for it, but like I say, I'm just ploughing onwards today. So when you ask for the next byte, we return that. So we look up byte number index, and that's our return that we're going to return. Whoops. And before we do that, we're going to move on. That should be self.index above, shouldn't it? Self.index plus equals 1. And this should be self.bytes. And the other thing we need to check is have we reached the end. So if self.index equals, or is a guess for like belt and braces, we'll say greater than or equals the length, then we return none. Otherwise, we know that we're allowed to move on one. We know so if it's either a greater than or equal to the length, or this is a valid thing to do, to look it up by index, then we increase the index by 1 for next time, and then we return the answer. Okay, I'm fairly convinced that that's iterator-ish like behavior. Now we've got this lex prop ident, which is what we were trying to implement. So we've been given one letter. Now we look through for more letters and end up building a string out of all of them. So that means that we know that B is from A to Z. So I think I can somehow make a char out of it, but I'll do it in here. So I think we can make a string from UTF-8, and that will be a slice of U8s that we're passing. No, what is it? It's a vec of U8. That seems wrong. What about from UTF-8 lossy? That would be now a slice. So now I can pass in, or we make a little slice which just has B in it. Like that. And the reason why lossy is fine, this one, let's just say this will never be lossy because we just checked in Lex that B is
from between A and Z. Format. Oh no, I'm not using the nightly compiler, so it won't wrap my comments. Okay. Okay, so we've made a string which just has one character in it. Now the whole point of what we were doing here is continuing through bytes to find more things, which are while bytes.next. What is it? It's like we need to get the next byte. So I guess it's while we get something, while we get some B out of bytes, then we add it to ret. Well, if it's okay, we add it to ret. So that's if it's in this range. Can we do this? Like we're trying to match. That feels really weird. We could do... Would it feel less weird if we did this? Otherwise, false. So basically, what I wrote before I think was right, because if let is actually pattern matching, but it was so weird I just couldn't cope with it. So we're doing a pattern match. If it's A to Z, then we're going to push. We should be able to push onto a string a char. Yeah. So we can make a char, I think, from UTF-8 loss C, maybe? No. It'll be from U32, maybe. And that would be, put just B. Is that going to work? We can just as that because well, in fact, we can probably into it, right? All U8s are U32s, trivially. And if it doesn't match, then we're gonna return and this is going to also return ret. Return OK ret, I guess. But it needs to do something, it needs to push something back, which we'll do in a second. Now, what are you moaning about? All kinds of things. Nothing's right. How is it a copy on... Oh, just from UTF-8 lossy, return a copy on right. Oh, goodness. Well, that's not what I wanted. What if we just make a new string and then we push one byte onto it? I guess you push one char, which is going to be... Oh, and this needs unwrapping because... char from U32, for some reason... Yeah, not all U32s are valid characters, but in our case, we know precisely that B is in a range A to Z, so we can just unwrap. We should probably do some kind of expect explaining. It should be B. We can turn it into U32 with just into. Stop my timer telling me to take a break. All right, so we've got the numbers of errors down to something less totally unreasonable. This should be just... What am I doing wrong here? This is not at all what I meant, is it? What I meant was, yeah, okay, this is the thing. If we found A to Z, we just push. If we didn't find A to Z, we should stop and we should return an error. No, we should... We're fine. It's not an error. Maybe there are no errors here. Just anything that's not A to Z means we stop lexing this thing. So that means we're going to break. But we should also put something back into the iterator. So put back B. Right, so the point is we pulled something out that wasn't an A to Z. So we should put it back again and then stop and return ret. That's what I'm going for here. So let's have a function called putback. None of this is tested. I feel so bad. I'm so sorry. We need to take in a byte that we're going to put back. And I guess we need some kind of... well, I guess we don't even need... We can just say go back one, right? Should we call it backup? No, that sounds like backup. Let's say go back. Just go back. It'll do. And we don't actually need to give what... We just need to say go back, please. Because of the way we've written this, we happen to know that we haven't actually lost any of the bytes we were iterating through. They're still there. We're just using an index to count through them. So go back is pretty simple. We should do some error checking though. If we're already at 0, taking one away would be real bad. If self.index is 0, put back before beginning of bytes. That's not good. Do not do it. All right. So now we can say, so just going over all that again. When we're parsing this multi-character string, we found the first character. That might be the only one there is, but we don't know. It's between capital A and capital Z with equals, so including Z. So we know it's going to be a property ident. But we need to find the other characters, so we call lex prop ident, pass in the first character that we found, and this iterator that we're allowed to modify. By the way, this never fails, so let's not have it return a result. Just to simplify our lives. And then when we're going through those letters, we got given the first letter. We've got this iterator-ish thing to move through. We know the answer is going to be a string. We know we've got the first character of that string, so we stick it in there. Loop through all the bytes until we hit the end. If we hit the end, we just return the answer. If we didn't hit the end, we got a byte. Check that byte. If it's A to Z, push that one into the answer. Otherwise, step back one so that that byte isn't lost, and then stop iterating. Will our test get any further? Well, yes, it died at character 91. No, sorry, it died at column 4 is what I'm going for. Because it didn't know what that character was, which I guess is an open square bracket. So I really am regretting not identifying more easily. Now, what did we call this? Prop value. Right, so then we're going to follow a similar pattern. So that might have felt like overkill for just grabbing a few more letters. But here, now we don't need the B because we know it's an open square bracket. So we'll just pass in
I don't think we should call it iter, but anyway, we're just passing this iterator, this changeable, and we could just call it input, couldn't we? Yeah, that's probably better. And then maybe we could call it input here too. And maybe move through should just be called input. Lex input. Something like that. And now it doesn't feel quite so bad that we've re-implemented iterator, but different, because it's not an iterator anymore. All right. So we need this other function, whoops, called lex prop value. So lex prop ident was looking for letters. Now we're looking for anything before a closed square bracket. So let's just jump back to the file format. So now we're doing prop value, which is an open square bracket and then some stuff that we aren't going to properly identify yet, and then close square bracket. So we're going to loop through. It's going to be quite similar to this. It's not going to make a string. It's going to make a vec. Oh, wait, that comment's wrong. It's the only thing we need to explain here is the unwrap. Let's just change that into A to Z was not Unicode. Right, we know that B is A to Z. So how is it not Unicode? Similarly here. A to Z was not Unicode. And let's just, if I've got two error messages that are the same, well, it probably means I should be sharing the code or something, but anyway, oh, what have I done? Oh, I've added some extra brackets. Yeah, if I've got two error messages that are the same, then I'll put something in them to make them distinguished when they happen, so I know which one it was. Probably overkill because the line number also gets printed out, but anyway. All right, so we have been given this input. We're looking for anything until we get... So we're going to copy this code and do it differently because it's going to return a vec of U8. Yep, like so. So when we push in, we don't have a B to push in, so nothing to push in at the beginning. We loop through the characters. Basically, if it's a closed bracket, we stop. And if it's anything else, I guess we don't need that. Then we just ret.push it. I've kind of reversed... Oh, we have to do it this way around because anything else is like is always the last thing. So if we found a closed square bracket, we don't even need to put back. We can just break. Oops, I ended up a long way up the screen. Yeah, because we don't. This square bracket is not useful for anything. We can just put it back. I guess we need some kind of to-do for handle escapes, because you can actually escape handle / for escaping. So sometime we'll do that, but not yet, because we've got no tests for it. All right. So basically what we're doing here is collecting all the characters which are not closed square bracket, putting them into our return value and then returning. If we hit a closed square bracket or we run out of input, then we finish lexing this thing. I guess if we run out of input, then that's an error if we didn't hit that square bracket. So I guess we'd just put in a to-do for that. To-do handle reaching here without hitting square bracket. This is an error. This is an error. Fine. Run our tests. Oh look, they get to the end and then fail because we've done something wrong.
Is it that we just haven't put a close bracket in the test case? Yeah, look, we lost the close bracket. Right, look, our test pass. We are able to lex this whole thing. So we have, it's like a basic game in SGF format. Parse lex is okay. Let us just to be sure that we're doing it right, let us pick up a slightly more complicated one, because when we come to parsing, we'll want to have things with nested brackets. So, nested game lexes. This probably already lexes. I didn't spot anything that was weird in here, but we'll see. We don't need quite so much of this. So we'll have, let's have the FF and the GM this time. And then a black move, and then a white move, and then a nested black move. And then a new line, because that's good. And then another nested black move and a white move. That looks okayish to me. And then we're going to assert some stuff about it. We won't waste too long on this because it would be nice to do a bit of parsing, wouldn't it? So far all we've done is lexed. We need to unwrap that. Okay, so it's going to be open bracket, semicolon, FF4, and then it's going to be GM1, then it's going to be semicolon, then it's going to be BAA again, then it's going to be semicolon, then it's going to be WBB, and then it's going to be another open bracket and another semicolon and a BBCC. No, just a BCC. And then a close bracket. And then an open bracket. Something that looks a bit like this. So it's going to be BHH and then WHG. And then a couple of closed brackets. So what was that? WHG. And then a closed bracket and then another closed bracket, and that's the end. Why doesn't it like it? Because I've missed out some commas. We should have had comma. If we'd had a comma here, that wouldn't have happened to us. Okay. All right, that might already work. No, it didn't like the character at column 18. Ah, which is a new line, I guess. Let's try. 18 characters to the right takes us at least to the end of the line. Let's try 17. No, why does... Oh, that's not right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. It is right. All right, column. Oh no. Oh, but these column accounts are wrong because we never went back and did our to-do. All right, we better put a bad character in after an FF, hadn't we? There's our error handling code. I bet you were yelling that at the screen a while ago. Invalid byte. Well, let's just say error column is correct after prop ident. So basically, if we put in FF brackets A, B, C, D, E, F, G. Let's just say after prop then. And then we put a question mark. That question mark's not allowed. And it's still on line 1, but it's now in column 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And let's put a comma at the end of these as well. My Rust format should probably say to always put that in or something, I don't know. Alright, so let's try a few tests. And our test fails because it says column 4, but actually it should say column 13. And that is because we have not been updating our column number correctly. Because we probably should be passing it in, because this is the weird... This is making me start to think these should be methods on some kind of struct. If we're passing in 2 mutable references to things, and we should pass in mutable reference to line even though we don't use it. Otherwise it's weird because we definitely should be using it. So mutable reference to column and line, and that means that line needs to be mutable because soonish we're going to make it work. So the point is, every time we consume a character, we need to add 1 to column, which means column needs to come in here. And line, which is unused. So I'll give it an underscore straight away. Right, and that's also needed for the other function, which is above it. We should make our minds up, so let's put this one below because it's below in the code, calling code. Oh, there should be star column. And in the other code as well, every time we consume a character, which is both these places, we should add 1 to column. So I guess if it's both these places, we can just do it there. Yeah, and then the time when we don't consume a character because we put it back, we don't change column. So I think that works. Yep, so now error column is correct. While we're here, should we do line number as well? No, you get the idea how we would do that. We'll do that later. Alright, so now our error message should be better. It says column 33, which I'm guessing is the new line character. So, how do we deal with new lines? Now, in this particular game, the new line happens not inside any kind of property or anything like that. It's in between brackets. So anything that's white space, according to the spec, anything that's white space gets ignored when it's outside of text, and inside text it gets converted to a space instantly. Anyway, so when we are looking through all these things, if it is a new line, now at some point I guess we're going to need to be able to handle different types of new line, because the spec says there could be /r/n or /n/r or /r or /n. But for now, we can just do nothing. Ah, no, because this... we're expecting to get a token here, but actually this character calls us to do nothing. So I guess this is going to need to return none, and all these others are going to need to return some, and we're going to need it to be an option that comes back, which is a pity. Maybe there's a nicer way of structuring this. But maybe not. It's a comma.
So now we've got token. We should just say if we actually had a token, push it into the thing. Otherwise, just carry on. We still add one to column, right? Where do we add one to column? Here. Yeah. So I think that's okay. Every time we've absorbed a character from input.next, then we add one to the column. Yes, okay. All right, so now we've got a very difficult to read diff saying our test almost worked but didn't quite. B 9797 semicolon W 9898. Oh, there's an open bracket. No, there's a missing close bracket, I think. So probably I just did the test wrong. So let's have a look at the test. So where were we? We were saying, where were we? We just done a white move. White BB, and it just says open bracket. So that close bracket's wrong. That shouldn't be there. That's why I had to add an extra close bracket when I was writing this test. Right? Yeah, okay. All right, so that all lexes. So great. I guess Jez would tell me I'm long overdue a commit. So what we did was made a lexer. Lexing for SGF files. I think that's all the lexing we need. Not sure. All right, so now we want to do some parsing. So I've had to put off. So something a bit weird about what we've done is that a prop value is just a vec of U8. Like it could be any bytes at all between these square brackets. And that's because different prop types have different things that are allowed inside them. So I think there's multiple layers of meaning. We've done lexing, which is just the tokens. The next thing to do is to build this into a structure of just properties, I think. And like the nesting of brackets. And then the next thing would be to look at the meanings of these properties and decide, is the stuff inside the square brackets actually allowed, and like translate it into like meaningful stuff. So I don't think we'll get to that, but hopefully we'll do enough parsing to say, this is a bunch of properties that constitute one like move, I guess. What are they called? What are they called? So it's a collection, which is like a list of game trees. The game tree is this bracketed thing, and then a sequence is a bunch of nodes. So yeah, this node is the word I was looking for. All right, so we're going to do this all in one file when really we shouldn't, because we are. Because you having to watch me break stuff up into modules is so painful. But what we will do is make ourselves a new test module for parsing, like so, and a new test function called. Well, let's copy all of our successful tests and make them about parsing instead of lexing. Empty game tree parses. Even though technically it shouldn't, but don't tell anyone. Right, so if we call parse, and we use the parsing functions we're about to write, then what this should produce is really, it will produce like I said, it will produce a collection of game trees. So let's say it produces a collection,
and inside that collection there's a game tree, and that's all there is for now. So it's going to be collection I guess we give the collections constructor a vec of game trees. So that means that these things need to exist. So let's just let's imagine that parse. So this is like lext, and this is like parsed, and we're going to call parse, and that's because parse exists. There it is. I guess it's going to return a result of collection, and I guess it's going to have some kind of error type, and it's going to take in tokens, which is whatever we get back from lex, which I think was a vec of token. So I guess it's going to take in, it can take in a slice of token, because you can, whoops, you can always treat a vec as a slice like that. Alright, what's it moaning about? Alright, no, it needs to be parse of lex of this thing, doesn't it? Looks like. What? But lex is, like, lex is down the bottom. Well, they should. Why does this say parse? Must have done some kind of misguided rename. Oh yeah, look, I renamed lex to parse. That's probably broken all my tests. Yeah. That was me not thinking straight. Now I've renamed parse to lex, I think. Yeah. Poor old me. Alright, where were we? Is that right now? We need to unwrap after lexing. And then shall we unwrap after parsing as well? Which we should probably also unwrap after lexing here. And then if we take a reference to it. I mean, why don't we just take in a vec by value? Because we took in the bytes by value, didn't we? When we were lexing. Let's just take ownership of those tokens. Alright, so parse is gonna produce a collection which I think is just gonna be a vec of game tree. And that means we need a game tree struct, which for the moment has nothing in it, I think. And we're going to need a parse error. And all of these things are going to need to be debug and partial eq, so we can use them in our tests. Alright, so let us just return a collection with nothing in it, which means that we need a new function for collection which takes in a vec of game tree, which is just sticks in itself. What are we doing here? Oh, this should be
we should parse and then lex. And then this variable shouldn't be called tokens. Let's call this syntax. Let's call this collections. Now, like I said, because there's two layers of this, we might decide that this should be like a naive collection, and then there's this like more complete collection that actually understands what's going on. But we won't worry about that for the moment. Okay, so our test fails because we're returning an empty collection, but actually we expect a collection with an empty game tree in it. So, how do we parse things? Well, basically we consume tokens, and in a similar way to the lexer, sometimes we just consume one, but normally consuming a token helps us understand we're in the middle of something else, so we need to then go off and suck more tokens until we reach the end of that something else. So I guess we're going to need a parse input that looks a lot like a lex input. So we could actually make lex input be generic. Because we're going to need to put back in a similar way, I think. Let's copy it for now and pretend that it's like specific to parsing in some way. Maybe we'll find that actually that is a useful property, and maybe we won't. So let's have ourselves a parse input. If nothing else, it's kind of easier to read if we know exactly what we're working with. Is that an excuse? That's an excuse. Let's call this tokens, and this is going to be a vec of interesting that was a slice of U8 that we were holding on to. Let's see how this goes. Let's make this a vec of token and an index. That's all we need. And then here we can just do this. That means that we don't need any kind of lifetime on this because it's owning the tokens. That's good because it means the next we'll be able to return a token, not like a reference to a token, right? No, because we don't want to suck it. We don't want to take it out of the. Should we return a reference to a token? Let's return a reference to a token. See how that goes. There should be tokens. So look up that thing. I guess we need to clone it. No, because we're taking a reference to it. So what are you moaning about? Oh, how is this? Oh, because I forgot to rename it. That's how. Alright, so this should be looking in tokens. And ret is, it's for some reason not got a reference. There we go. Yep. Go back, put back before beginning of tokens, I guess. All right, so we've got this this iterator-like thing that we can put things back in. We need to loop through the tokens. So it's a very similar. The reason why I like this is it's a similar structure to the lexer. If we do it this way, so let us. These line and column probably need to come through with the token, but we won't worry about that right now. I've been really good about making our errors, at least giving an example of how our errors would remember some information about where we are in the file. But I think it's time for me to give up on that because it gets really irritating, and who wants to watch me do a good job when we could watch me do a bad job? Okay, so where have we got to? Forget the columns, as I said.
ret is going to be, I guess, a collection. Then we can return OK ret and we're all good. And okay, so collection, I guess this should be called from when we're creating it from a vec of game trees, and we should have another thing called new, which Clippy would warn me should be like, there should be a default implementation of collection for this. But basically I'm saying game trees is an empty vec if you just call new, which is not done that way, it's done this way. This is a collection, this is a tuple type struct with round brackets. That's what they call that, a tuple type, I think. So this should be called, this should be a new empty collection. You could have collection colon on default or something like that. So we go through the tokens. And if there is one, then we do some kind of match on this token. And it won't be any of these things. It will be one of these things. And actually the only ones that are valid at this point when we're parsing a collection, because parse is actually parse collection, right? The only things you're allowed are open bracket. Everything else is an unexpected token. Because we only get to this code, which means, I guess, probably don't need the if let anymore. We probably just want to get a token. This shouldn't be a token now. This should be a game tree. And if we didn't see an open bracket, then we're going to return some kind of parse error. Otherwise, we did get a game tree out. We can put it into there. So parse error, unexpected token, and the unexpected token is going to be token. And ideally, token itself would have the line and column in it. So that's how that information would get into that error message, but we haven't done that, and I can't be bothered. Oh, this I guess should be add game tree. Let's make ourselves a method called add game tree on a collection, which just pushes no self.0. So the vec inside us is self.0. Push game tree onto there, which is of type game tree. This needs a mutable reference to self. Okay, now, what are you moaning about? No, let's just have a copy of token in on that unexpected token error message, which means, I guess, we need to clone token, which means the token needs to implement clone. Yep, okay, let's have token implement clone. There's no problem with that. And sometime maybe it'll hold a reference instead of a value type, in which case that will be a cheap clone. All right, where have we got to? Yeah, this, once we've got an open bracket, we need to do something. So what we're going to do is we're going to make a game tree. And then we're going to parse the rest of the game tree using the input, and why don't we just
called parse game tree, and it can construct a game tree inside it. I think that was a slight mistake of what I did earlier, maybe, that I guess this could fail, so we'll think about that in a second. But yeah, we made the token outside of this lex prop ident, and maybe the best thing would be if lex prop ident returned a prop ident. That kind of makes sense. But let's do a structure like that, at least for our parsing, and probably we should do that for our lexing. All right, so yeah. We should pass in a mutable reference to input here. So let's have it expect one. Now, at the moment, parse game tree, all it expects is that it's going to find a close bracket and anything else is an error. So we're going to do something very similar to this to parse a game tree. Get the next token. I mean, this really is like a no, but it's, yeah. I still don't like the fact that we're passing input into something else. So anyway, we get the next token. If it is a close bracket, then we're all good. We're not going to do this. And if otherwise, well, then there's no breaking. We are going to find a close bracket and return a game tree. Or we're going to find something that isn't a closed bracket and return an error. No, because so this needs to be a result type. Because this might fail. So this means this needs to be an OK game tree. So it's a bit funny at the moment because all we're doing is looking for a closed bracket, and we will be looking for more stuff, so it'll probably make more sense then. And now we need to do it. I think if we just do a question mark on this, it'll propagate the error upwards. All right, what are our warnings about? I'll go back not being used yet. And this is only used in test. All right, fine, we can make it only visible in test. The other warnings are okay for now. When we run our test, it passes. So we are able to parse an almost non-existent game tree, just bracket bracket. So now let's try and parse something a bit cleverer. I think the really simple thing would be a single property. Do I mean property? Let's check what they're called. Sequence node. I guess I mean a simple node. Yeah. Simple node parses. This is going to actually be quite a lot of all the work we need to do. But yeah, so we have some examples of simple nodes here. Something like, actually, this would be better. Because then it's got two characters. Oh, well, this has got two characters in the, I don't know. I mean, I guess that doesn't matter anymore because we trust our Alexa. So how many characters are in that property ident doesn't even matter. We trust our Alexa, right? All right, so that should come up with a game tree in a collection, obviously, but the game tree should contain
a property, and that property is a prop ident. So it's a property with an ident of ff and a property value of the bytes for the string 4. So game tree needs a new method, and we need this property thing to exist. No, just let me make a new. So import game tree for new, returns a self. And maybe this should be from as well. I don't know. Probably should. Yeah. Because it's in here, we're going to pass in a bunch of properties. I think that's how this works. No. What was it? It's a game tree includes a sequence of nodes. So this should take in nodes. And that means our test is not quite right. So a game tree is just a vec of nodes, I think. Nodes. And a node is, what is a node? A node is a semicolon and then 0 or more properties. That makes sense. Yep. So that means a node is a list of properties. I think that's right. And a property has a ident and a value. And yeah, like I say, at the moment this is all very undefined. It's just going to be a string for the property ident, and the value is going to be a vec of u8, and then there'll be some way of transforming these properties into things that make that have more meaning. Right, so and okay, node and property need to have debug. Alright, what are you moaning about? Our game tree should have a new for like just make an empty one of me. Let's add that. Again, should be implementing default if I'm going to do a new method like this. But yeah, basically an empty game tree just has an empty vec inside it like that. What else is it moaning about? So this game tree this should be a game tree made from a vec of nodes, and there's only going to be one node which is made from a vec of property. Is that right? Did I get the number of brackets right first time? Game tree is for a vec of nodes. A node is made from a vec of property, right? No, does node not have a from yet? Okay, that's our problem. I think that's why the compiler is confusing. Should I not be calling it from? because that's like, I think string is string from, I don't know, we'll call it from for now. So we put this, you can make a node from a vec of property. I mean, I arguably, what is this? Arguably, I could just expose the, I could construct it directly by just saying node bracket like that instead of having some kind of from method. Okay, and then property needs a new function. Nearly there with the boilerplate, maybe. Makes an empty property. Or not empty. It has an ident and a string. I mean an ident and a value, which we pass in. Yeah, there's not a lot of point in these constructors. You could just directly construct the property. But sometimes you kind of regret not having made a new function, I find. Alright, so this needs to be a string and this needs to be a vec. That's one reason we could have made the new function do this bit for us, but anyway. Right, so when we run the tests, something goes wrong because we have an unexpected semicolon. Because game tree doesn't yet know how to actually parse things. When we're parsing a game tree, by the way, this could be like game tree : parse or something, but I don't like mixing up the kind of abstract representation of a game tree with the concrete logic of how to parse one, so I don't mind it being separate. Alright, so we were expecting a closed bracket only. If we find a semicolon, we need to do something else. And what we should do is have an empty game tree here. And make it mutable. And if we find a closed bracket, return it. And if we find a semicolon, do something else, which is similar to what we did before. We need to call some kind of parse. Oh, what is it? It's called a sequence. I guess it's parsing it. Its sequence is kind of implicit. It's parsing a node now because it found a semicolon. So parse a node. Pass in a mutable reference to input and put the answer, yeah, so let node equal that, could return an error. And if we got one back, then we're going to add a node somehow. Alright, so let's have a parse node function. Returns the result of node or parse error, I guess. It was already a mutable reference, so we can just pass it in here. And helpfully, my editor had made it a mutable reference to a mutable reference instead of saying, "Hold on, that code makes no sense." All right, and then we're going to do the same thing again. This function is going to look really similar. You can see why people end up writing parser generators instead of writing parsers, right? Because the code law looks really similar. Well, now we're making a node, which means that we need a way of creating a new node. Which is just an empty vec of properties. Okay.
So parse node. Okay, so parse nodes exists, but we don't yet know what to do with anything. So let's just say, yeah, we'll just fail. And we want to provide an add node method on a game tree. And this is quite straightforward, right? We could have these all could have just been vex and things, but it feels right to represent them. Simple as that. No, self.0, because this again is a tuple struct. This again is only used in tests. And this one too. All right. So hold on. We're not using go back yet. I feel like we're going to. Yeah, probably when we get. I don't know. We'll see. All right. So we are parsing a node. No, right. What happens now? So yeah, we got a prop ident, and we are panicking at line 181 because that's where we. Oh no, that's no use. We're panicking at. Okay, we've lost where we're panicking, but where we're panicking, I assure you, is when we're trying to parse a node, matching on a token, and we got a token which was a prop ident. So that's good. If we got a prop ident, in fact, this really shouldn't be a loop. Parsing a node, we know exactly what we're expecting. We find a prop ident, and so it's more like it's something like we need to get hold of, we don't even need node new. We need to get hold of an ident and a value, and then we're going to return right at the end a node new, which takes in the ident and the value, which we've already got hold of. And now to get the ident, we get the next token, and if it's not, so we need to basically we always need token to be next, so we can do some kind of map, some kind of okay, or yeah, if it's not, if there wasn't another token, then it's a parse error, and the type of the parse error is going to be unexpected end of file, I guess. I guess we could say what we were expecting. Well, let's have eof when expecting prop ident. That's explicit enough, right? We got to the end of the file when we were expecting a prop ident, so we'll create that variant in a second. So we got hold of a token. That token should be a prop ident. Otherwise, we fail. I mean, I actually kind of prefer let else over. So maybe the bit above should also use let else. But anyway. How does that look? No, I've really broken everything. Because that should just be semicolon. Actually, I think I want to use a let else. So I'm going to do let some token equal input.next else. Which do you prefer, viewer? I like this because I can use it in the next section and like follow the same pattern. Some people don't like early returns, and I can really see that. I love like functional code. This should be returning an error. And so, like, functional code requires us to essentially have one logical line. But this does read pretty well. All right, so what's the problem? Node, there shouldn't be a node new. Like, how are you going to make... Oh, what? No, I'm talking rubbish. Parsing a node requires us to parse multiple properties. So what we're doing here is parsing a property. Right, so let's actually just have it return a property. Property. And now the only thing that's wrong here is can we star that? Maybe. We don't have a value yet. So while we're parsing properties, let's parse properties. So now the next token should be a prop value. And yeah, so we need to get the next token. So let's call this one ident token, and this one value token, just to be clear. So we get hold of value token, end of file when expecting prop value is the error. Yes, add that variant please. And value should be but we got them out of the parse input, so we need to clone them. I suspected we would need to clone them. Like so. And now, like, I'm really thinking this is inefficient. If we were caring about efficiency, we really need to think carefully about not having these own their data, but being references instead. Yeah, but don't you see that I've finished using input? I've still got a reference to something that came out of next. That's what's going on here, isn't it? But I've stopped. I no longer have any need for ident token. And ident... Okay, now hang on. I can clone this earlier. And then this... Yeah, the problem is I'm cloning this late. So that means that I'm holding on to a reference. I think I need to do it here because otherwise I can't read it in here. There we go. Alright, so anyway, right, so that's parsing a property, but the point is, when we parse a node, we should look for multiple properties. We could actually kind of put back the semicolon and then, because like every node, no, every property within the node starts with a semicolon. So let's put the semicolon back, which means I need this. Oh, it's not called put back, it's called go back. So I'll add back in, go back. so that parse node has input that starts with a semicolon, parse node should return a result of node or parse error. And we just go through. It's another one of these loops. We loop through saying if you find a semicolon, then parse the rest of the property. So this is a node. We are going to need node new after all. And we go through the tokens. And if we find a semicolon, then parse a property, and we're going to add that property to the node. Oh, come on. We're going to add that property to the node, which means that we need to have an add property function. So, oh no, self.0.push property. Right, run our tests. They failed because we hit a close bracket. Yeah, so what we've failed to do is stop parsing our node when we didn't get a semicolon. So actually that's not an error. That's just, we've just finished can we break? I mean, this should just be while let. While let that. Right, is that the pattern I should be using in other places? And then we need to return something, yeah. So, is it just that, okay, ret goes here. And this is just break. Maybe we should be using while let in some other places. Anyway, we go through. Every time we find a semicolon, that means that we're starting a property. So we read in the rest of the property and add it. Otherwise, if it wasn't a semicolon, we break. But before we break, we need to push it back. This is why I really like this pattern for writing a parser. You can just like stick something back in the stream of tokens that are coming at you. If we didn't do this, we would have to return this thing that we pulled out of the stream and then use it later, or we would have to peek. So instead of getting the next thing out of input, we'd have to say peek the next thing, which means have a look and see what it is, but don't actually remove it from the stream. And that's the way most people implement stuff like this. I like the putting back. Hey, look, it passes. So let's just recap what we've actually done here. So we've parsed a game tree which contains a property which has an ident and a value. We've done pretty well. What we don't have is the whole tree structure. So maybe we can do that. How does the tree structure work? Basically, a sequence is not just a sequence of nodes. It's a sequence. It's a node, and then possibly a whole game tree, not just another node. That's what's going on there. Yeah. All right. So I think we can do that. So let's find ourselves a more simple example, less simple example. So let's see a nested node parses. And should we get this massive one? Yeah, why not? Okay, so let's just do the big example. Hopefully it'll be fine, right? Just lex all of this and then unwrap.
I have to spell Lex without a semicolon in its name. And the answer we get back should be... it's only a single collection. And it contains a game tree, yes. It's only a single game tree. Obviously, it's only a single collection. It's always only a single collection. It's a single game tree, which contains a few nodes and then another game tree. So game tree being just a vec of node no longer works for us. Game tree is going to need to be a vec of, I guess we can call it node or game tree, which means we've got an enum called node or game tree. I think this is the way to represent this. And if it's a node, it contains a node, and if it's a game tree, it's a game tree, and that means, unfortunately, this is a recursive data structure, so we can't do this. So first of all, this needs to be debugged and stuff like that. But secondly, if it's a game tree, because this is contained within a game tree already, is this what it's telling us about? No, at some point it's going to tell us we're not allowed to do this. But let's fix the compile errors and eventually it'll come. So we can no longer make a game tree from a list of nodes. It has to be from a list of node or game tree. And if you add a node, that's fine. We'll do the work for you. We're going to add a node or game tree of type node. To our list. So then when we're making a game tree, it needs to be a node or game. Every time we add a node, is actually a node or game tree, : node brackets. Node. Where does node end? Here? No, here. Yep. All right. Yeah. So every time we were making a game tree out of just a list of nodes. Now it's a list of node or game tree. Did I explain that well enough? Let's have another look in a second. What are you worrying about? Oh, game tree's not used yet. All right. So yeah, if we look at this structure, a game tree is either a sequence of nodes is a sequence of nodes and then potentially more game trees. Okay, so it's not actually what I've implemented, because I'm allowing you to intermingle nodes and game trees, and that's not actually right. It's a list of nodes and then a list of game trees, which could be empty. So I think I need to change my mind. It's a good thing I checked. So just to explain this in a more concrete way, each game tree consists of all these nodes, which are the things that start with semicolon. But then at any point, instead of a semicolon, you can find a bracket, which means that there is a nested other game tree inside this game tree. But the point is, you can't then have more nodes. You can have more game trees because the branches, like, you've done a load of nodes, and at this point you're branching off into two. That's what this means. And so you can't then go back and do some more nodes because you've already started a branch. That's basically what that means, I think, if I understand it right. So I've actually changed my mind. A game tree is not a vec of node or game tree, because then that means nodes and game trees get intermingled. A game tree is some nodes. This kind of is simpler than what I was doing. And some game trees, which come after the nodes. We don't need this enum anymore, so apologies if that confused you. And all of this is just more simpler and more direct, so I hope I'm right. Game trees, but we're still going to have the problem that it's a recursive data type, so we'll get to that and fix it. Sorry if I'm blowing on the mic. I removed the pop shield from my mic foolishly. Okay, so game trees is a vec of game tree. Yeah, again, what's the point of this constructor method? I don't know. Then adding a node just adds a node. And soonish we're going to need to be able to add a game tree. In fact, let's add that now while we're here. Game tree. So add that game tree, because we're going to need it in a minute. Now people are moaning again because we're back to, we should have just had a node. A vec of nodes rather. And now it needs to be followed by a vec of game trees, which we'll just have as empty here. And yeah, this is the complicated one, which is going to have both nodes and game trees in it. So first it has a node. And then it's going to have, well, for now we'll just do an empty one. So so we make a vec of nodes, and then we make a vec of game trees, which is going to, at some point, going to have something in, I think. All right, what's unused? Add game trees unused. Fine. When we run the tests, we fail because there was an unexpected token prop ident GM. Interesting. Why? Where are our tests? There we are. So, okay, so multiple properties. Okay, so I've actually messed this up. So before we do this difficult thing, we've got a simpler test case, which is multiple properties in one node. Multiple properties in a node parse. So that's just going to look like ff4 gm1. Like that. So I think, does this, whoops, what have I done there? Oh, yeah, commenting that out wrong. Let's add it back and comment it out properly. All right, so yeah, we'll think about our property. I think I've done this totally wrong. So when we run that, it fails because it was expecting a semicolon because my expectations were wrong. So this should be multiple properties. This is why you test, because I've done it completely wrong. Again, apologies if you were yelling at your screen. So just getting the test to expect the right thing before we make it pass. So
It should have an FF property with value of 4 and a GM property with value of 1, because when we parse a node, it can have multiple properties in it which are not separated by semicolons. So I think I've just made a completely wrong assumption here. So parsing one property, we just look for an ident and then a values, which is fine. But when we find a semicolon, we don't just want to parse one property. We want to parse many properties. So I think what we should do is have this return an option of property like this. And if we didn't find an ident token, we just return none. And if we did, then we'd return some. And now we're going to need to go through parsing lots of properties in a while loop. And each time we get one, we add it. Was it that easy? That seemed really easy. What are the warnings? Add game tree is not used, and okay. And this is no longer an error that can happen. But we can still get an end of file in the middle of a thing. There also should be a bunch of other errors, like hit the end of file when we're in the middle of a game tree or something like that, which we haven't covered those cases. We're not enforcing that you have to end it with a bracket. Okay, so we got an unexpected token close bracket. Oh well, and maybe we're about to enforce that. So when we're parsing a game tree, now if we find a close bracket there, we're happy. But I guess we were inside parse node, and if we find a semicolon, that means we're parsing a node. Yeah, so we don't need a while let. Parsing a single node is not a while, but I think we're parsing multiple nodes here. So this should be like, what we're returning is like a vec of nodes. Is that fair? Or alternatively, we could have some kind of while loop here and do the same type of thing. Yeah, well, we could do this. Well, while we've got a node from parse node, then add it to our thing, which means this returns an option of node. But as soon as we find there aren't any more nodes, instead of dying, yes, this should only return. This shouldn't be a while loop. This should be just get hold of the next token. Otherwise, return none. And now we've got a token. We match it. And yeah, it's either a semicolon, in which case we're going to read in all the properties, and the answer is going to be a node. So I guess we make the node here and return it. Or it's not a semicolon, and we're going to return okay, none. Is that right? The only question is if there weren't any tokens at all, is that okay? Not really. But I guess it's okay. So yeah, if we hit the end of file here, someone ought to be complaining to do complain that we hit the end of the file in the middle of well, it's not in the middle of a node, it's when we're looking for a node, but we are in the middle of a sequence, I guess, or a game tree, because a game tree is just a sequence is just what a game tree is made up of. But we won't handle that error. We'll run our tests, and we're still getting an unexpected close bracket. Interesting. So simple node is failing. So I guess let's think this through, because the simple node test down here is pretty straightforward. So we're looking for multiple semicolon and then property. We find something that's not a semicolon. It's a close bracket. We push it back into, what we've just implemented is that we're parsing node. We push that semicolon back in, and we come out of parse node. And then surely we then hit this type thing next time around the loop, right? This should be wildlet. No, but then it should be, but let's not mess. Okay, so where are we hitting this unexpected close bracket? How many times do we actually return unexpected token in our code? There's parse property. Oh, the problem is when we're parsing a property. Yeah, if this wasn't the token we expected, that doesn't mean that we've died. It just means we've hit something that we, like the close bracket in this case. So actually this should be an okay none as well. And we need to put back. We need to go back. Input dot go back. Yeah, so we were looking for another property. And this is this is the to do error, because we should not hit end of file here. Should not hit end of file here. This is the expected case. Actually, we were thought there might be another property, but actually there isn't. In that case, there's a closed bracket, or maybe there's a semicolon. So we should just stop looking for properties because there aren't any more. Hey, look, that test passes. So now we've got the nightmarish test. And we haven't yet done nested game tree, so this is definitely not going to work yet. So we've got an invalid character at column 34, which is the new line, I believe. What? No. Look. A tab has appeared, or a space. I guess a space has appeared. Yeah. All right. So there's an unexpected open bracket. That's exactly what we're hoping for, right? We're trying to parse. We're looking at a sequence. Well, we're looking at a game tree. So we've got what is it? We're looking at a game tree, which is a sequence, and then potentially a game tree. And we're only dealing with the sequence part of it, not the game tree part of it. So what we need to do when we're parsing a game tree, which is here, we need to look for a bunch of nodes, which is what this is, and then we want potentially there's an open bracket here, and we kind of want to check that we're only adding nodes. We want to do this and then later look for game trees. That would be
correct way to do this. So that would mean we. So was it? Did we hit this unexpected token here? Doesn't really tell us, but probably, hopefully, that would be where we would hope for it. So what we can do, the naive thing we can do, is just look for a open bracket. And if we find an open bracket, we can do something like this, except we're parsing a game tree. So we're calling ourself recursively, which I think is okay. Oh, but this is not an option. It definitely is going to find a game tree. So I guess this is just... Okay, we found an open bracket. We're just going to parse a game tree. And then we're going to add the game tree. To ourselves. What are you complaining about? I've done some silly wrong syntax. Yes. Okay. So this is fine, except if we find a semicolon and we've already added some game trees, that's an error. So one thing for us to do would be to just keep track of that. It needs added game tree equals false. If we actually do this, then it's true. And if we've added a game tree here, this is an error. So we can say something like, it's a parse error that it's a sequence after game tree error, right? So it should be sequence and then some game trees, no sequence allowed after. So, and I guess we should provide the token so that you know where this happened if the token it had that information in it, which it doesn't. But yeah, all these errors should have tokens inside them. Oh, but in this case, there isn't a token, so I take that back. Okay, clone it. All right. So that was not a very elegant way of doing it. It's potentially better if we could somehow start by looking for nodes and then move on to looking for game trees. And it would be better. But I think this works. So what happens? All right. I think we might have done it because that test probably doesn't have. Yeah, the test doesn't actually express correctly what's going on. So it should be a node containing multiple properties. So this is a GM and a 1. And then another node. This time just containing one property, which is that BAA thing. And then another node. Which is the WBB one. Oh, have I messed something up?
What's wrong with you? Oh dear, I did mess something up. That's better. Okay, so that was 3 nodes. And the game tree then allows you to supply some game trees. So we've got two game trees. First one just contains a node with a property in. This should be a vec of nodes. And an empty vec of game trees, because there's no more game trees inside that game tree. Yeah, and there also isn't any more in the other one. Well, that's okay. We don't need to go too nested to test this probably, hopefully, maybe. So that first game tree is a BC, contains that BCC. Another level of nesting would be kind of nice. And then this contains 2 nodes, both of which are single property nodes. Yeah. So it's a vec containing a bunch of nodes. And then another empty vec. Shall we just to do it? Let's to do it. To do test deeper nesting. All right, so that, hang on, that final thing was a BHH and a WHG. BHH and a WHG. Oh wow, our test passed. Okay, so that thing here has parsed out into a bunch of game trees. Well, a game tree containing a bunch of nodes and a couple of other game trees inside it. And that recursive structure has worked, and we didn't have to deal with the fact this was a recursive structure because it's in a vec. Is that why? Yeah. If I just said there's one game tree in this game tree, it doesn't know how much space to make. It doesn't know how big a game tree is now because it's like it's infinite sized. A game tree contains a game tree, contains a game tree, contains a game tree, contains a game tree. So that's no good. But a vec is a fixed size thing which points to a bit of memory that's got some game trees in it or whatever. So that's fine. So we didn't have to deal with it being a recursive data structure, which is very cool. So we've done our tests pass. We have managed to parse things which represent Go games like this into a very general structure where there's no meaning at all to this GM or this FF or whatever. So the next stage, which maybe we'll do in another video, will be to understand these things, because at the first layer of approximation, the properties, let's see if we can find this. There's a list of properties, and each of these properties is like yeah, here we are. Each of these properties has a type, right? So the different types have rules about what is allowed to be in there. Yeah, it's this thing I'm talking about, these property values. So some of these properties are allowed so-called simple text. Some of them are only allowed like a number or some very specific thing like a move, which is that AA. That's like the coordinates on the board that you're moving or something like that. So yeah, the next phase is to like make sure all these different types are represented in our code, and we convert things into, say, simple text or a move or whatever.
And then there would be, you know, future phases would be like turning that data into like a Go game that you can view, like maybe just the current board, or step back and forward through the moves, or try the different branches that there are. So I hope you enjoyed parsing SGF files and learnt a little bit about this quite odd looking, but in the end, I suppose, reasonably simple data structure. Let me know whether you want to parse more things, and if so, what you want to parse, and see you next time.